Begin. Okay, well, let's begin then. Thank you. So in this lecture, I just wanted to start off looking at piecewise smooth ODE systems with two intersecting switching manifolds, and then make some remarks on adding noise to the system, and then we'll look at equilibria and get on to boundary equilibrium bifurcations. Okay, so it's a simple example where it's a two-dimensional system. We've got two switching manifolds. So x equals 0 is a switching manifold, and y equals 0 is also a switching manifold. So the system has four regions, within each of which the ODEs are smooth. In fact, in each region, the ODEs are constant. It's a piecewise constant system. But some interesting things can happen when we perturb it. Okay, so let's do a calculation of an orbit of the system. Let's start off at some point on the positive x-axis. So following vector field in the fourth quadrant. X dot's -1, y dot's -1. So we're going to go down into the left at 45 degrees, and we're going to hit the negative y-axis at the value of negative x naught. And this is a crossing region, and in fact, all parts of the switching manifolds are crossing regions for this example. So now x dot is -1, y dot's 1, so we go up and to the left 45 degrees. Now we're at -x naught. And then next we go along 2 and up 1. So x naught over 2. And then lastly, go along and end up at some point. What is this point? Let's see. So we go along 1 and down -2/5. So perhaps if we have the equation for this line. So this line it's a straight line. There's the general equation for a straight line. I know that the slope of this line is -2/5 because I'm going along 1 and down 2/5. And C is the y-intercept. My y-intercept is x naught over 2. Okay, so I figured out the equation for the line. I'm trying to determine where the line intersects y equals 0. So if y equals 0, then x equals x naught, and I've got a 5 and a 4. So this value is 5/4 x naught. And the point is that this value is bigger than x naught. So I've gone around one revolution, and I've gone outwards. If I was to go around again, I'd continue to go outwards, and so on. So what we conclude is that orbits of this system are spiraling outwards. And that's really all it does. So then we could smooth the system if we wanted to. Linear smoothing. So the simplest way I think we could smooth is to replace the switch manifolds with little bands of width, like the 2 epsilon, and then just make the system continuous across those bands. I won't write out the equation for doing that. It's in the notes. It's just takes a bit to write out. So we've got lines at minus epsilon, plus epsilon, and also for x, minus epsilon and plus epsilon. Just smooth the system linearly across the boundaries, and you get a continuous system. But surprisingly, it has slightly more complicated dynamics. I don't need to do it again. So what you find is when you smooth it, you get a stable equilibrium somewhere in the middle. Yes, yeah. Yep. So the idea is you've got your a function is discontinuous across the switching manifold. Right. You've got your discontinuous function, and we're smoothing it, so we'll just go backwards to the left by epsilon, and to the right by epsilon, and then we'll stick in a straight line. So that turns the discontinuous function into a continuous function. And it doesn't have to be horizontal lines; it could be some curves there. Yes, that's a very general and very simple way of making a discontinuous function continuous. So when you just have one switching manifold and you do this smoothing, nothing really interesting happens. But here we've got two switching manifolds, and we do this and we get something interesting. We get a stable equilibrium surrounded by an unstable limit cycle. And then things spiral out the other way. Yeah, so by smoothing the system, we introduce some new dynamics. In this case, we introduce a limit cycle. My colleague Mike Jeffrey at University of Bristol would call these hidden dynamics. The limit cycle is kind of hidden and only appears when you smooth the system. That's right, yes. So the idea is we take the limit epsilon goes to 0. The system I've done on the board is actually so simple that the structure of the dynamics is independent of epsilon. As you take epsilon smaller and smaller, you just get that the limit cycle just gets smaller and smaller. Nothing else changes. Right. 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 How does it work? Yes. Yes, yeah, dividing by epsilon. That's right. You can see that in this picture, that the slope of this line is, you've got to divide by epsilon. Yeah, so it blows up, but the dynamics is nice. It's okay. Okay, so let's move on to adding noise to the system. I just want to start in one dimension. I'll just make some general comments first of all. So suppose we have some one-dimensional ODE and we add noise. So mathematically, there's more than one way of sort of adding noise to a system. I think the most natural thing to do is to write down what's called a stochastic differential equation. Plus f d2 plus. I just don't want to go into the technicalities here. Just think intuitively. We've got an ODE and we're adding some noise. Alpha represents the noise amplitude. But really what I mean is this stochastic differential equation, where W is a standard Brownian motion. So that the noise is Gaussian white noise. And okay, so if we choose some initial condition and solve, but because we've got noise, that the point that we get to after some time t is not deterministic. There's it's a random variable. So there'll be some probability distribution associated with where we go. So I'll let P be the probability density function for that. Probability density for it's the probability density function for the value of x at some later time t. If you haven't encountered probability density functions before in dynamical systems, you probably did somewhere in statistics. Probability density function for a normal distribution or a Gaussian. So it looks like that. What's that? P of x is, what is it, 1 over 2 pi sigma. Where is it? Square. That's the formula for the probability density function of a normal distribution with standard deviation sigma. So if you want the probability that your variable lies in some interval, what you do is you integrate the density over that interval. But the integral over the whole domain has to integrate to 1 over the whole real line. Okay, so P is a probability density, so it has to be greater than or equal to 0 for all values of x and all values of t. P. And when you integrate over the whole real line, you have to get 1 for all values of t. Okay, so let's suppose that our orbit starts off at some given initial value, x0. So in that case, the probability density function is it's an infinitely steep density centered about x0. We call this a delta function. You encounter delta functions in engineering when you want to describe some idealized impulse. And what we'd like to know is we'd like to know how P evolves with time. So initially we've got a delta function, infinitely steep. And as time evolves, what happens? Given that formulation, so the evolution is governed by what's called the Fokker-Planck equation. Equals FE Okay, so this is a partial differential equation, but because P is a function of x and t, I could expand the brackets, d plus. So once I've expanded the brackets, if you ignore that middle term, you've just got the heat equation or the diffusion equation, which you've probably encountered in PDEs. Hopefully you've got an intuition as to how the heat equation goes. It just diffuses. Things just diffuse, which is what the noise is doing. It's having a diffusive effect. And you've just got this extra term which involves F that incorporates the drift, the effect of the vector field pushing you along in some direction. Okay, so let's look for a steady state solution. I'll get down here, so if a steady state solution to this would be something that doesn't change with time. That's what we mean by steady state. So in the Fokker-Planck equation, we'd have a 0 on the left-hand side. So now P is just a function of x. Now I'm back to a nice ODE. Yeah, so depending on what your function is, as time goes to infinity, you might settle to a steady state solution. So if the PDE is too difficult to solve, then maybe the ODE is tractable. If there's So as an example, let's consider the one-dimensional analog of our piecewise constant system. So we're just in one dimension here, so f of x, we'll say it's got some particular value AL for x negative and a different value AR for x positive. Let's assume that AL is positive, AR is negative. So that without noise, orbits are just going into x is 0. Draw. I could draw a phase portrait, I suppose. My phase space is a line. I draw that so. Orbits on both sides are converging to the origin in finite time. Okay, so when we add noise, we do all this. So what's the steady state solution Where am I? Got that the steady state solution satisfies this equation at the bottom. We have a little bit of a problem in that our function is piecewise. So I really have to consider, but when I'm solving this, I have to consider x negative and x positive separately, and then I have to join them together at x 0. So to do that, just use the fact that p has to be continuous at x equals 0, and then I've also got a little jump condition which tells me how the derivative changes at x equals 0. I won't write that. Just the jump condition tells you how the derivative changes at x equals 0. Effectively, the net flow of probability on each side of x is 0 has to be the same, or has to be the same flow of probability on each side. ALP. Okay, so let's see if we can compute the steady state solution for this example. Start off with x negative. The function f is just the constant AL. This is a second order ODE. It's a linear ODE, and we know all about linear ODEs. I could reformulate it as like a two-dimensional first order system, and I'll have a 2 by 2 matrix, and I could compute the eigenvalues of the matrix. I'll skip all the calculations. But we get two different linearly independent solutions. Just a constant is a solution to this, and also this particular exponential is a solution. However, I need p to satisfy this equation, that the integral has to be 1. So I could possibly have a constant. I have to have the exponential. X negative. Okay, so what I've found is that for x negative, that the steady state density p has to be some multiple of that exponential. I'll call my multiple k. Do the same calculation for x positive. You get the same thing, but we've got AR instead of AL. And it's so just get another exponential. But we have to have the same constant k because we need the density to be continuous. 0. And there's a jump condition, which it turns out is automatically satisfied for this one, which is helpful. What does this look like? So remember, AL is positive, AR is negative. So I've got increasing exponential and another decreasing exponential. So that's what the density looks like. So for a piecewise constant, one-dimensional ODE with noise, steady state density is a piecewise exponential. Has to integrate to 1, so you can use that to solve for k. I'll leave it for you to do the integration. Okay. So what's the form of P? Right. That's a good question. So you've got some value of x naught. So initially, the density is a delta function. So it's 0, and it's infinity, and then it's 0 again. As time evolves, it sort of turns into that, and whoops, can't be negative. And then it goes that way, and then eventually, as time goes to infinity, you get that. Now, there is an analytical formula for what it looks like there. The formula is pretty horrible, but it does exist for this case. Okay, so let's do the same thing in 2 dimensions. Yeah. I'll use my white chalk for some general comments. I want to go to the right of where the screen is going to come down. X. Oh, F of X plus. Okay, so now we'll suppose that F is a 2-dimensional nonlinear vector field. And we can do the same sort of thing. We have the Fokker-Planck equation in the same kind of way. But instead of del del x, you have a nabla, but you're taking the gradient. And so if P is a steady state solution, P of steady state solution, steady state, or PDF, I would say. Over there, steady state solution. Here is E. It's the same thing, but you just have nablas for your gradient now. Okay, so this is supposed to be in 2 dimensions, so nabla is del x, del y. F is a 2-dimensional vector field, so F has 2 components, F1, F2. 0 is F1, P, 1, del 1, F2, P, plus P. Okay, so in 2 dimensions, this is what it comes out to. Yep, so you've got that the last term is alpha squared over 2 times the Laplacian, which describes diffusion. And then these 2 terms capture the drift, the effective vector field F. So if we do this for our piecewise constant vector field at the start, F1 equals, and it's got 4 pieces to it. Each piece is just a constant, A1, B1, A4, B4. For my 4 different quadrants. Yeah, so you put this all in and you get a PDE It's not an ODE anymore because now it's two-dimensional. So it's a PDE in X and Y. 0 is A, I, E. Yeah. Okay, so in the ith quadrant, this is what the PDE is. And I think it's a fairly simple PDE, right? It's just, you've got this Laplacian plus a couple of linear terms. I mean, the AI and BI just constant. I could bring the AI and the BI outside the brackets. So I think it's a very simple PDE. Unfortunately, I don't know how to solve this analytically, because we have to have a jump conditions appropriately on x is 0 and y equals 0. That the derivatives have to match up. Yeah, so it's an elliptic PDE boundary value problem. It's two-dimensional, and I don't know how to solve it. At this point, I'll get the screen to come down if that's possible. Aha, look at that. Should all just magically work. Yeah, so we got this two-dimensional PDE boundary value problem. Don't know how to solve it analytically, but I can certainly solve it numerically. So that's what I can show you. So here I've got a system. It's like this, but just has some different numbers. I'm just using some different numbers so that the origin is stable. So without noise, orbits spiral in. If I didn't have that, then the steady state density wouldn't exist. I need the origin to be stable so that when I add noise, I get a nice density. So here's what I've computed numerically. I've got x on the horizontal axis and y on the vertical axis. Different colors correspond to different heights of my density. So the dark red in the middle is where is the highest value of the density. Yeah. Okay, so that's enough about noise. I'll move on to the next topic. If that's okay. Okay, so now we're going to think about equilibria of piecewise smooth systems. Okay, so here's our piecewise smooth system with one switching manifold. So a regular equilibrium. That this is what we mean by an equilibrium of either FL or FR. So a regular equilibrium is a point x star for which either FL of x star is 0 or FR of x star is 0. So the regular equilibrium is said to be admissible if it lies on the correct side of the switching manifold. So in the case of FL, to be admissible, we need H of x star to be negative. If it lies on the wrong side of the switching manifold, then we say it's virtual. But it's not an equilibrium of the full piecewise smooth system. And in the special case that it lies on the switching manifold, we call it a boundary equilibrium. You might like to call these points fixed points. I call them equilibria. I like to reserve the word fixed points for when you're dealing with maps, but that's just me. Okay, in the lecture this morning, we saw the sliding vector field. So the sliding vector field itself could have an equilibrium, and such an equilibrium we call a pseudo-equilibrium. A pseudo-equilibrium is a point at which the sliding vector field is zero. If the pseudo-equilibrium lies on a sliding region, that's what we need here. If it lies on a sliding region, then we say it's admissible. It could be either a attracting sliding region or a repelling sliding region. Sorry? A pseudo-equilibrium is any point that satisfies this equation. Usually, a pseudo-equilibrium is an isolated point, just like a regular equilibrium is usually just an isolated point. But you can imagine a line of equilibria, just like Victor has a line of fixed points that is degenerate bifurcations. Yeah, so pseudo-equilibrium is admissible if it belongs to sliding region, and it's virtual if it belongs to a crossing region. It has to. So really, this is the definition of pseudo. So what is Fs? That's the question. Right. So I should remind you about Fs. That's the sliding vector field we had this morning. Okay. Yeah, so but when you write out your equation for the sliding vector field, it is possible to have this case, because you just sort of blindly solve this equation and you end up with some number, and it could happen that number lies in a crossing region, just in the same way that a regular equilibrium could be virtual. No, so the first condition is that this one is either attracting sliding region or repelling sliding region. And this one is a crossing region. I probably should have written that up there. Okay, so let's look at an example. I think regular equilibria are fairly straightforward. You know how to compute equilibria, so that's fine. Pseudo equilibria are what's new to you. So let's compute pseudo equilibria for this example. What do we do? We'll need to figure out the sliding vector field Fs, and we've got a formula for that. Fs involves VL and VR. We need to compute VL and VR, and those are given in terms of H. So what is H? I could take my function h to be this. You could take it to be something, you could take it to be some scale multiple of that, I suppose. The point is that this function is 0 on the given line y equals 2x. So the gradient vector is 2 minus 1. And so that's a VL is this. I've never encountered such a long blackboard. So I should remind you what we're working towards. It is VL minus VR. All right, so there's our all-importance formula for the sliding vector field that we saw this morning. So VL is, well, I'm taking the dot product of 2 minus 1 and 3, 1. So I've got 6 minus 1 is 5. Okay. And 5 is a positive number, which means the vector field on the left is pointing towards the switching manifold. And in fact, I could probably see that already from these numbers of going along 3 and up 1. So. My vector field looks like that. VR, so I've got 2 times minus 2, and then minus 1 times x minus y. And what's that? Minus x plus y. 1, 4. Okay, so here's my VR. Remember, we only care about VR on the switching manifold. So I want to evaluate this on the switching manifold. So I'll substitute y equals 2x. Okay, so on the switching manifold, VR is x minus 4. And this morning you learnt that folds are where either VL or VR equals 0. So this equals 0 when x is 4. So I've got a fold at this point. Is it a visible fold or an invisible fold? Let's have a think, I suppose. So I would sketch the vector field nearby. So at this point, my vector field is tangent to the switching manifold. X dot's negative, so the vector field has to be pointing down and to the left. As I increase x, this becomes positive. So VR becomes positive, which means I'm going away from the switching manifold. If x is less than 4, it's negative. Going towards. So my two orbits have to be doing this. My tangent trajectory will be on the left. So it'll be an invisible fold. Okay, so here's what the vector field looks like. I can see from my sketch that this is an attracting sliding region, whereas up there I've got a crossing region. Right. Good. So I think we're ready to evaluate the sliding vector field now. So on. So on the switching manifold, x dot and y dot are given by this, which we've got 5. Okay, so I've done VL is 5, and then I've done FR. FR is this, but I've substituted y equals 2x because I'm on the switching manifold sigma. So I've substituted y as 2x, so this is minus 2 minus x. That's what I've got there, and the rest is straightforward. So you can simplify that. It's a vector. It gives us x dot and y dot. But the sliding vector field it's effectively one-dimensional. I only need one equation to describe it. So since I've got x's here, I'll just write the equation for x dot. So x dot is the first component. So I've got 5 times minus 2, and then minus 3 over 9 minus x, minus 3x plus 2. Okay, so here's x dot on the switching manifold. I've managed to reformulate my sliding vector field from 2 dimensions down to a nice one-dimensional equation. All right. Okay, so finally, I think we're ready to find pseudo-equilibria. Pseudo-equilibria are where this equals 0. And straight away, we can see x has to be 2/3. If x is bigger than 2/3, then this is negative. So if x is bigger than 2/3, it's x dot is negative, so x is decreasing. If this is less than 2/3, this is a positive. X dot's increasing. So here's my pseudo-equilibrium. It's a stable pseudo-equilibrium because all nearby orbits converge to it. Equilibrium. So in summary, we've got one pseudo-equilibrium located at x is 2/3, y is 2x, so therefore y is 4/3, and it's stable. It's also admissible because it lies on a sliding region, not a crossing region. Okay, so where are we for time? Okay, so I'll have a break from talking and let you tackle an exercise. Exercise 6.1. I'll give you a few minutes to think about that. Exercise. Okay, so I'll just go through this on the board fairly quickly. So we could first look for regular equilibria. So where this equals 0, you get x is -1, y is 0. So we've got a regular equilibrium here. It's on the left, so therefore it's an admissible equilibrium. You could compute eigenvalues and eigenvectors. It's just a two-dimensional linear system. You find that the eigenvalues are plus or minus 1, and the eigenvectors have slopes have 45 degrees eigenvectors. So the regular equilibrium is a saddle. Okay, so then, yeah, and this system on the right has no equilibria because it's constant. So I'll take my function h to be just x. Grad h is 1, 0. So then VL is 1, 0 times this vector. I'm just looking on the switching manifold. So on the switching manifold, x is 0. So I can put x as 0. Well, it multiplies by 0 anyway, so maybe that wasn't so necessary. Just get y, and then VR comes out to -1. And I can plug everything into the formula for the sliding vector field. And so, of course, you'll see x dot is 0. I've got minus y plus y is 0. X dot has to come out to 0. And y dot, what have we got? Sorry, what did I do? Oh, I see. Yeah, you're perhaps a little bit ahead of me. Sorry, I haven't written down y dot yet. Minus 2y plus 1, what do we say? 2y plus 1. And on the bottom, I've got a y plus 1, which doesn't do anything really. Yeah, so then we could look for pseudo equilibria, which are where this equals 0 and y is a half. Very good. Equals 0 implies y is a half, so that's up there. What else? I've got a fold where this equals 0. So y equals 0 is a fold. That's a triangle. It's an invisible fold because the tangent trajectory is on the right. And on the right, I've got -1, -2, so that's what else can we do? Is it stable or unstable? Okay, so if y is bigger than a half, this is negative. Y dot's negative, so y is decreasing. If y is less than a half, positive. And I forgot to identify my attracting sliding region. Attracting sliding region is above the fold at 0. For y negative, it's a crossing region. So my pseudo equilibrium lies on the sliding region, so therefore it's admissible. And it's stable. Okay, so I've got one regular equilibrium, it's admissible, and it's a saddle. And I've got one pseudo equilibrium, it's admissible, and it's stable. As I wrote in the exercise, you could look at the basin of attraction of the stable equilibrium, which is this one. So that the basin of attraction is defined as all points whose forward orbit converges to the equilibrium. Right, so nearby points certainly do. Anything up here converges. Points up here go to the switching manifold and then they slide down. I have a problem over here. Over here I'm going down off to minus infinity. So the boundary is going to be this line going into the saddle. So the boundary of my basin of attraction is this. So here's my basin of attraction. And the boundary of the basin of attraction is the stable manifold of the saddle. That's a fairly usual thing to happen. But when you've got multiple attractors, the boundary of the basin of attraction is often the stable manifold of the saddle. Okay. Okay, so last thing for today is we'll look at boundary equilibrium bifurcations. So what is a boundary equilibrium bifurcation? Okay, so we have a piecewise smooth ODE system. It's got some switching manifold sigma, and let's suppose it's got some regular equilibrium. As you vary the parameters of the system, your equilibrium will likely move a little bit. And so a bifurcation will occur when your equilibrium collides with the switching manifold. So we vary a parameter, call it mu. The regular equilibrium collides with the switching manifold. Changes from admissible to, at the bifurcation, it's a boundary equilibrium, and then it becomes virtual. So this bifurcation is boundary equilibrium bifurcation. It's sometimes been called a discontinuous bifurcation. So this is the analogy of a border collision bifurcation that you've heard Soumitro and Victor talk about for maps. So for maps, instead of an equilibrium, you have a fixed point. And as you vary a parameter, the fixed point collides with the switch manifold. And that's what we call a border collision bifurcation, sometimes called a C bifurcation, back in the old Russian literature. Okay. I think this is the simplest bifurcation possible for a piecewise smooth system. That's unique to piecewise smooth systems. Piecewise smooth systems can exhibit all the bifurcations of smooth systems. So piecewise smooth systems can exhibit saddle node bifurcations and hop bifurcations, etc. But this type of bifurcation, it's specific to piecewise smooth systems. And I think it's the simplest such one. So tomorrow we'll spend the rest of today and tomorrow, we'll spend quite a bit of time looking at boundary equilibrium bifurcations. So, okay, so let's sort of work towards a general theory for boundary equilibrium bifurcations. So we consider systems of this form, so just with a single switching manifold. But because a boundary equilibrium bifurcation is a local bifurcation, but we only care about what's happening to the dynamics locally. So the system could have other switching manifolds further away, but those are not important. But for simplicity, we'll suppose that the bifurcation happens at the origin. So this point's the origin. So I need my switching manifold to pass through the origin. So I need h of the origin to equal 0. So can I draw a picture for that? Here's my origin. This is h of x equals 0. So h of the origin has to be 0. I also need the switching manifold to be non-degenerate. So grad h has to be a non-zero vector at the origin. So normal vector, it's not very good normal vector. Let's try again. So grad h is a normal vector to the switching manifold. But we need grad h to be non-zero so that h of x is 0 is actually a n-1 dimensional manifold. So this vector, I'll call it zeta. It's going to be important. Okay, so our system varies with a parameter mu. We'll suppose that a regular equilibrium of the left system collides with the origin when mu equals 0. So that's what this condition does. So when mu equals 0, the origin is an equilibrium of the left half system. Okay, and so with that, I can expand the two pieces of my vector field, FL and FR. I can expand them about x is 0 and y is, and x is 0 and mu is 0. It's useful to do a Taylor expansion because it's a local bifurcation. I just care about the dynamics locally. I just care about x near the origin. I just care about mu near 0. So f of a x plus b mu plus 42. So A is an n by n matrix. B is an n-dimensional vector. The point is that I can't have a constant term. I can't have a constant term because of the condition above. And then I've got plus order 2. So by order 2, I mean quadratic in x and mu. So how should I properly write that? It's like order, like the norm of x squared plus mu squared. I think that's what I mean. Okay, so there's no such condition on FR. So that generically, there will be some constant vector. So C is a constant vector. And then next I've got linear terms, which for FR, linear terms are higher order. And as we'll see, they're not going to be important. Okay, so we've written down some general equations to describe a boundary equilibrium bifurcation. So what we'll do is we'll calculate equilibria and see what we find, I guess. So regular. Let's look for regular equilibria. Well, the system on the right, FR, that's not going to have a local regular equilibrium. If I set this equal to 0, then yeah, I get something higher order. So it's only FL that we care about for regular equilibria. 0. So regular equilibria satisfy this equation, so then I can solve for x. Plus order. Great. A is an n by n matrix. Let's assume that A is invertible. So then I get this with an A inverse. And the higher order terms are going to contribute order mu squared there. Assuming this is so I need to assume that A is invertible. And with that assumption, we get a unique regular equilibrium locally. Okay, so here's our unique regular equilibrium. We'd like to know, is it admissible or is it virtual? Okay, so is it admissible? Well, let me give it a name. I'll call it XL. I'll call it XL because it's an equilibrium of the left system, and it's a function of mu. Okay, so just from the definition of admissible, so it's admissible if H of it is negative. And so we evaluate H. What do we know about H? Well, we know that H at the origin is 0. So when I expand H in a Taylor series, I don't have a constant term. H of x is, well, it's actually a gradient zeta transpose x plus, and then plus terms that are quadratic in x, and so on. Zeta transpose minus A in the B, yep, plus order. Okay, so to leading order, H is zeta transpose x, and XL is minus A inverse B mu. So put all those together. Yeah, that's minus zeta transpose A inverse B mu plus order squared. Okay, so this tells us that the quantity we need to look at. We need to look at zeta transpose A inverse B. that thing's going to tell us for what values of mu it's admissible or virtual. However, before I do that, I'm going to write A inverse as the adjugate divided by the determinant. I'll say what I mean by that in a moment. Adjugate B determinant mu plus order mu squared. Okay, so if you don't know what the adjugate of a matrix is, you might have encountered it in sort of undergraduate linear algebra when you were learning about inverses. I mean, if a matrix is invertible, then A inverse is adjugate divided by determinant. So adjugate is determinant times inverse. Unfortunately, this equation only works if A is invertible. But what's nice about the adjugate matrix is it's well defined even if A is not invertible. So for example, for a 2 by 2 matrix, A is A, B, C, D. The adjugate of A is D minus B minus C, A. You recognize that from your formula for the inverse of a 2 by 2 matrix. I think that's all I need to say on the adjugate. In some tiny footnote in my notes, I gave the proper definition. Okay, so got zeta transpose the adjugate of A. That vector I'm going to give a special name, call it rho transpose. So let rho transpose, zeta transpose adjugate. I'm trying not to cross the line there. Yep, so I've run out of space. I go, what do I need? Oh, sorry. Equals. Okay, so we get minus rho transpose B divided by the determinant of A mu, and then plus. Great. So I like to think of rho transpose B, which rho transpose B is just a number. We've got dot product of two vectors. Rho transpose B, we need that to be non-zero. We need this to be non-zero in order for this value to change linearly with respect to mu. So as long as this is non-zero, and as long as A is invertible, then the derivative of my equilibrium with respect to mu. Let me start again. As long as this is non-zero, then as I vary mu, the equilibrium is going to move linearly away, which is what we want generically. So this condition is our transversality condition. Transversality. This is the transversality condition or the boundary equilibrium bifurcation. If instead this was equal to zero, then we'd have a very degenerate scenario. Every bifurcation theorem should have some transversality condition. I've seen Victor's put up theorems for bifurcations, and in there there's some derivative has to be non-zero. There'd be a derivative with respect to mu, kind of like what we've got here. That has to be non-zero. So for non-degeneracy, we've really got two conditions. This rho transpose B has to be non-zero, and also the determinant of A has to be non-zero, so that we actually have a unique regular equilibrium. So I haven't answered this question yet. is admissible if this thing, right, so we need this thing to be negative, so perhaps I'll go back over there. Yeah. So the idea is that we're varying the value of mu. So as we vary the value of mu, the sign of this thing changes. So as we vary the value of mu, the equilibrium changes from being admissible to virtual. So it's admissible. From mu such that minus rho transpose D A mu. I think. In the notes, I gave this an even simpler name. I just called this alpha L mu. I'll come to that. So we'll talk more about that again, but let's go onto the sliding vector field. So and we can compute this. Well, we'll write down the sliding vector field, and then that's probably a good place to stop. So equals zeta. So VL is given by this. Grade H is zeta, and FL is AX plus B mu. Plus the higher order terms. Equals zeta transpose C. And then VR is just zeta transpose C. Okay, so we've got another non-degeneracy condition. We need zeta transpose C to be non-zero. So this tells us we need the vector field on the right to not be tangent to the switch manifold at the bifurcation. If this was equal 0, that would be a special degenerate case that we don't usually want to worry about. Fs equals VL FR minus VR alpha over VL. Okay, so let's put everything into our formula for the sliding vector field. V transpose A plus B mu FR C. Fine. Zeta transpose C FL plus for the 2 bottom zeta transpose A plus B mu minus C plus order 1. Yeah. Okay, so I don't have much more to go on. Okay, so I've just put everything into the formula for the sliding vector field. One thing you might notice is that when I put in VR, for VR, I've got the zeta transpose C plus order 1. And so the order 1 here is the same order as VL. So this is a higher order term. I don't need to worry about that guy. I can simplify a little bit. So on the top, both terms have an AX plus B mu. So I can factor out the AX plus B mu. Space equals AX plus B mu. And have some stuff that I'm factoring out. So what else? I've got a zeta transpose C, right? Yeah, that's right. Oh, no, so it's a C zeta transpose. That's move the C around there, right? You can think of it as putting some brackets here. This is just a number, so I can move the number on the other side of the C. So I've got a C zeta transpose divided by a minus zeta transpose C. And then my other term, I've just got minus zeta transpose C divided by minus zeta transpose C, which is a 1. But I need the identity matrix, really, because this thing is a matrix. This is a rank 1 matrix because I've got a column vector times a row vector. Column vector times a row vector gives me a matrix. Yeah, and then plus order 2. Good. Okay, so here's my sliding vector field for my formulation of boundary equilibrium bifurcations. So the next time we'll continue on from here, we'll analyze this a little bit, and then we'll eventually get to a normal form for boundary equilibrium bifurcations. I think that's enough for today.